I hope this session is going to be useful too. In today's e-commerce driven world, every minute, thousands of parcels and packages are getting delivered worldwide through the postal delivery networks, transforming online click into delivered promises. And behind every successful delivery lies a bunch of complex network of moving assets. For example, delivery van, roller cages, containers, and many other IoT devices operating 24 by 7 across cities and countries. Hello everyone, I'm Amit Singh, working as a Senior Solutions Architect at AWS. Today I'm going to talk about PostNL's journey to real-time IoT asset data management, along with my colleague Lorenzo Nicora, who is a Senior Streaming Specialist SA at AWS, and Charu, who is a Lead Software Engineer at PostNL. During this session, we are going to talk, of course, about PostNL, the business requirement behind building the IoT platform itself. We are also going to discuss about the challenges with IoT system, the real-time asset data management, and finally, we are going to share the learning and key takeaways. So PostNL is an universal postal service provider with headquarters in the Netherlands. It has three main business units: postal delivery, parcel delivery, and logistics for e-commerce and cross-border solutions, or CBS. On a typical weekday, PostNL delivers millions of parcels and letters in the Benelux region. So Benelux as in Belgium, Netherlands, and Luxembourg. Next, so you must have seen these orange color boxes near railway stations, public spaces, shopping malls. These are known as automated parcel lockers. These are very secure, and customers can pick and drop their packages to automated parcel lockers 24 by 7. Now, talking about some numbers, there are more than 1,100 automated parcel lockers, over 5,800 retail points, and more than 10,000 mailboxes in the Benelux region. Also, PostNL is not just a postal delivery company. It is an integral part of modern commerce infrastructure connecting business with the consumer through the postal delivery network. Now, before we talk about the IoT platform, let's talk about some key business requirements behind building this IoT platform. So, the first business requirement is need for real-time visibility to improve the operational excellence. So on a typical weekday, PostNL processes more than 7 million of parcels and letters, which moves through different devices, different IoT assets like roller cages, containers, handheld devices, tippers, and many other IoT devices. So it's very important to track those packages in real time to ensure a timely delivery of the package and parcel. Next, PostNL is also aiming to implement IoT digital twin and facility management to improve the performance efficiency and predictive management. As of this year, PostNL is having or using more than 400,000 IoT assets. And they want to track these IoT assets in the real time, as in how those assets are working, are there any performance requirement, or if a maintenance is required, right? So they can do the predictive maintenance also of those IoT assets, and hence they are planning to build the digital IoT twin. Next, PostNL is also targeting to reduce the lost and misplaced assets. So what is happening is during the logistics operations, thousands of assets are getting misplaced. And this is due to the human error. So for example, when the roller cages are moving from one geofence to other geofence, from one sorting center to other sorting center, it is getting misplaced due to human error, as I said, right? So PostNL wants to track these assets in the real time. Also, PostNL is planning to optimize electric vehicle operations, which is also one of the sustainability goals at PostNL. So as of this month or this year, PostNL is using hundreds of electric vehicles, but they are aiming to add more than 4,000 electric vehicles to their logistics operation by 2030. So they want to track the charging status, battery health in real time which will improve or maximize the delivery efficiency and also reduce the delivery vehicle downtime. And at the center is security, because PostNL is using multiple asset types. There are billions of data flowing from one asset to other asset, so they want to ensure that data which is flowing is secure. Now, let's look at the IoT landscape, and starting with the collection points. So the automated parcel lockers which they are using are equipped with IoT sensors. And these IoT sensors are used to secure the access and also to track the occupancy monitoring. The point of service systems are also connected for real-time transaction processing, and all this data flow is happening on AWS. By doing this, they are enabling the real-time visibility and management of the packages. Now, moving to the logistics network, you can see a person is trying to push a cage or container kind of thing. So these are known as roller cages or roller containers. So PostNL has equipped Bluetooth-enabled beacons they have placed underneath the roller cages to track these roller cages in the real time. And finally, moving to the advanced sorting centers, alongside the roller cages or roller containers, PostNL is also using IoT-enabled tippers, handheld devices, and many other IoT assets. And finally, this entire IoT landscape is running on AWS, and all the data processing is happening on the AWS. Now, the key point here is every touch point in this IoT landscape is source of billions of raw IoT events, which PostNL is processing later. Now, with this, I'll hand it over to Charo to talk about PostNL's IoT platform.
Thank you. My name is Charo, and I am working as a lead engineer in PostNL IoT platform. And now I would like to go a little bit deeper. I would like to show the PostNL IoT platform, the place where we connect digital world to the physical world. So I would like to show a very high-level architecture diagram starting from the edge. So we are connecting different assets from physical world, like electrical vehicles, which are helping us to optimize our carbon dioxide emissions as a part of our broader sustainability goals. Every day we are increasing the number of the electrical vehicles day by day, but it also sometimes brings some other challenge, but also advantages. So by having those electrical vehicles, we can also optimize the routing by the data we get from the cars, like battery data, by combining the charging station availability in real time, which means in near real time we can create dynamic routing algorithms to make our operations more efficient and sustainable. But sometimes things are not fancy as electrical vehicles, but we have also other kind of assets, like roll cages, and they are a very important part of our logistical operations, because without them, we cannot move any stuff from one place to another place. They are not very fancy, but luckily we have some Bluetooth beacons, which we can also give some connectivity to those devices. And we have currently more than 400,000 roll cages, and we are tracking them to improve our operations and make logistic operations better by knowing where they are and how many of them are available or not in any time, in any location. So this is a very crucial, because they are a very important part of logistics operation, and without them, we cannot do any logistics operations. Next to it, we have also other kinds of devices. They are not like moving devices, but they are tipper devices, which we are using in sorting centers to tip our roll containers, basically to make our operations easy in terms of the workload. But this is the edge part of our platform. We have also ingestion side. Ingestion part is basically the place where we connect data from edge to the cloud environment via different channels, like it can be MQTT, or it can be APIs, or it can be pool, or it can be similar solutions. But this is where we get the data from the edge, and we also sometimes do pre-filtering or cleaning the data, and also giving the structure to the data. Next to it, we have actually this is the core of our platform, which we are doing to hold the magic. We are doing lots of aggregation, lots of anomaly detection, lots of optimization with the data we have. But we have also right side, which we provide the data products for our end consumers. So, for example, we are providing the asset state product, which the consumers can understand the latest status of an asset at any time. This is like simple API, but which is very useful if you only want to focus on the latest state of an asset. But next to it, we have also some kind of event-driven products, which we can provide whether an asset is available or not by doing some telemetry calculations based on the IoT detections we get. We have also some kind of historical data which we need to provide for routing algorithm optimizations. If you would like to have also compliance requirements, in any case, you need to store the historical data for many requirements. But we have also some products which are providing the geofencing events for our downstream systems, which they can build some logic based on some actionable events. For example, if you know when an asset leaves a PostNL location, and if you receive the event, you can create many different logics to start other processes based on those kind of events. But this is a journey, or this is a long journey, while connecting different assets with different devices. Also, even with different sensors, there are lots of possibilities. And also, there are lots of challenges we had during this journey. I would like to talk about this journey. So, one of the most common thing in IoT system is actually filtering the real valuable data from noise, because we are getting billions of detections from the edge, but some of them very repetitive and some of them doesn't add any value. So it's very difficult to catch the real true signal. So, and it's even more difficult to do this in real time if you would like to provide real-time actions for your logistical operations. So we had to come up with a solution which we need to focus on what matters. So we have the data, or we have the data on the edge, but we need to convert this data into the information, which is actionable information for our downstream systems to make the operations more efficient. As you all know, everything always fails. So, but when it comes to IoT, this is more common, or this is more challenging even, because we have 100,000 of IoT devices, assets on different sensors, and they are moving one location to another location, maybe sometimes one country to another country, and it's even more challenging with the moving things. And of course, we are also having lots of connectivity issues. So, what is the issue with the connectivity issues? The problem is it creates lots of late or out of order data. But the thing is, not all this late or out of data is not garbage data. It may still provide value. So our challenge became we need to process all incoming data, even if the data is late, even minutes, even hours or seconds. Another thing, as I just said, we are operating, or we are using hundreds of thousands of devices in our logistical network. So they are attached to roll cage, some of them are attached to electrical vehicles, or some of them are attached to the other kind of devices. So it's very also common to have those devices to have battery powered, which means, and they need to have always sufficient battery. So the thing is, we can understand, or we can detect when the battery is empty, but it might be too late. Especially if you don't have direct access to those devices immediately, if they are operating in one location, which is very difficult to access. We had to understand their diagnostic or management data, maintenance data in near real time, before they happens an issue. So we had to prevent failures before they disrupt our logistical operations. Another thing, every day we are receiving billions of IoT events from different places, different devices, different sensors. Some of them are location updates, some of them are temperature data, or some of them are just heartbeats. So because of the volume, this brings a huge challenge for us, not only because of the number of devices, but also because of the data we receive every day. So the key is, or the challenge is, we need to scale our system without losing any performance. So the data we receive must continue to flow. Our alerts should trigger on time, and APIs always must stay responsive. So, and we have to do all this very cost efficiently because of the scale we have. Scaling easy, but keeping is fast, reliable, and also affordable is where the real challenge is. Another thing, as you can imagine, we have different type of assets, like, as I said, electrical vehicles, roll cages, tippers, and there are lots of possibilities, and they can have different, very different devices. So the thing is, we had to support all kind of assets, what kind of device they have, so what kind of sensors they have, and it's not an easy thing. So the system we built had to support all kind of different assets and devices and sensors. Another thing, the products we built, the data products, somehow we got the data from the edge, we converted data into the actionable information, but the next step is to deliver data to the correct business unit in the correct format or in the correct access pattern. Sometimes we had to use events if our consumers really need to build some kind of actions based on the event data we provide. But sometimes we had to also provide APIs if you need to access the data on demand, just when you need it. But sometimes we noticed that even a simple API or simple dashboard next to simple API can deliver lots of value. So just only listing asset data can make our operations very easy. And of course, the historical data, like for the data lake solution. So this is also a very necessity if you want to also provide historical data or if you want to provide some kind of compliance requirement. So those are some of the major challenges we had in the last couple of years with the IoT platform. I tried to summarize. Now I am going to hand over to my friend Lorenzo, and he is going to explain how we solved those challenges with the real-time streaming. Thank you.
Thank you, sir. So, hi everyone. My name is Lorenzo Nicora. I am streaming specialist solution architect here at AWS. And my job today is bringing you from the problem space we have been so far into the solution space, looking at how PostNL implemented their real-time asset data management in the IoT platform. But let's start focusing on the core of the IoT platform where the stream processing happens. But before going to the how, let's look at the why. So why did PostNL use stream processing at the core of the IoT platform? Well, we need to look at the major characteristic of stream processing for understanding that. So first of all, stream processing means processing data continuously. You process records as they arrive. And this is opposed to batch processing, for example, when you're actually processing data periodically. And this is the real core difference between batching and streaming. And the other characteristic is that you process data while it's in motion. It means that you don't have to stop the data in some data store to do the processing, move it again in another data store to do the processing, and so far and so on, as you do normally in a batch pipeline. In stream processing, you process while the data is moving. This doesn't mean the end destination of a stream processing pipeline cannot be a database or a data lake. This is completely fine and actually very common. But the difference is you're not stopping the data, you're not putting the data at rest in the stages of the pipeline. And the combined effect of these two characteristics is actually reducing the time it takes to have the output, or as you can say, reducing the latency. And the business benefit of this is actually quite evident at this point, because PostNL can have a result in a matter of seconds, or even less in some case. They can know what is happening to an asset right now, not a minute ago, not an hour ago. And knowing what is happening to an asset right now means they can create insights in real time. And these are insights that are actionable. Actionable means they can act on them immediately, doing, for example, alerting or implementing automation to do something automatically when they detect something is happening to an asset. So let's look at the roller cage solution that we learned was the first one that PostNL implemented. So we learned that the roller cages have a beacon installed on that, and the beacon is transmitting among many other sensors. Actually, we are just focusing on the two most important one. They transmit the last known position, the position where the roller cage is, and whether it's loaded or not, with a simple switch at the bottom, checking whether there is a box on that or multiple boxes on that. So with just these two information, PostNL can effectively know where available roller cages are at the moment. So they can move roller cages where they're needed. As simple as that. I'm oversimplifying, of course, but this is the gist. Also, another important use case, we learned that actually many roller cages get misplaced because they're moved around countries, and they get lost. So actually knowing the last position of the roller cage allows PostNL to do investigation and recovering the roller cage most of the time. Also, there is another, well, small use case, but actually very important, because the roller cage is, the beacon is also transmitting its own battery level. And just with this information, this information allows PostNL to preemptively do maintenance and replace the beacon before the battery is completely exhausted. So let's look at the ingestion of the roller cage. So roller cage actually use a dual ingestion path. So because beacons use Bluetooth low energy to communicate, they installed across and throughout the fulfillment center a number of fixed BLE gateways that are receiving the signal from the roller cages. But also, to extend the coverage, PostNL is also using the mobile phones of the operators as gateways, as mobile gateways. So effectively, the signals coming from the beacons are received both by the fixed gateways and the mobile phones of the operators. And the difference is that the mobile gateway are actually pushing the data into IoT core, backed by a Lambda, while the fixed BLE gateways are actually calling an API and pushing into a REST API exposed by API gateway, again backed by a Lambda, but both commonly push the data containing the raw events into a Kinesis data streams as JSON that then feeds into the stream processing stage we are going to see in the next slide. So independently from the source, the result and the format of the event is actually identical and goes into the same Kinesis stream. So the processing stage is centered on Amazon Managed Service for Apache Flink. Let's park this part for a minute, we will see it later, and let's focus on the other two components. So we have learned that the raw events are coming in from Kinesis data streams, but also Flink generates actionable events that goes into another Kinesis streams. And what is peculiar about Kinesis data stream? Well, Kinesis data stream is part of those services that are called stream storages. Stream storages are different from messaging system. Why are they different? Well, first of all, messages are retained after being consumed. This is different from messaging system, typical message broker, where a message is typically deleted after being acknowledged. This is not happening in a stream storage. And in a stream storage, messages are retained for a configurable time. In Kinesis, it's 24 hours by default, but it can be extended up to 1 year. Also, the consumer can replace data from a stream storage, and when a replay happens, this happens deterministically, always in the same order. Every time you replay, you get the data back in the same order. And this feature is essential for stream processing engines such as Apache Flink to support the strong consistency guarantees they provide. So getting back to our actionable events that Flink produces into the Kinesis data streams, they actually then they actually then fan out to multiple downstream systems to support different use cases, each one using a different technology based on the actual use case and the actual query pattern that is required for that use case. So, for example, availability is backed by Amazon Elastic Cache Redis, and a Lambda is writing into that. Asset history is actually supporting two different use cases. So, the top one is for supporting dashboarding, and the storage is based on time stream. Time stream is a time series database. But for doing any long-term analytics, for example, for training machine learning model, PostNL is using a data lake. I mean, that's the most common tool people are using. And in this case, well, the data lake, of course, is backed by S3, and they're using Amazon Data Firehose to feed from Kinesis into S3. And finally, as we have learned, geofencing. Geofencing is actually using Amazon Location Service. So Amazon Location Service allows PostNL to know which area of the fulfillment center the roller cage currently is, but also to be notified when a roller cage moves between one area to another. Let's look at the electric vehicle now. Electric vehicles are similar. We see have actually some very relevant differences. Electric vehicles, of course, are sending a lot of data points, a lot of metrics. But let's focus on the most important one. So the most important one is the battery charge level. PostNL is also currently working on gathering telemetry from the charging station. And combining these two information, and of course with the position of the vehicles, with the position of the van, PostNL can optimize the routing of the delivery van. Again, oversimplifying, but this is the focus of the use case. Looking at the ingestion, as you can see in here, the ingestion of the data from electric vehicle is completely different from roller cage. PostNL is actually using a third party for getting the data from vehicle over mobile network. And the third party is exposing an API with this information, this raw data, and PostNL is polling constantly this API with a simple scheduler based on event bridge, and the implementation is based on a Lambda that is calling this API, getting the data, and then publishing the data as JSON again. This is similar to roller cages, into Kinesis data streams. In the processing side, again, we have similarity but differences. The core is, again, Amazon Managed Service for Apache Flink that consumed from a Kinesis stream. But in this case, instead of emitting actionable event, let's say cleansed event, the application, the Flink application, is actually directly updating a Amazon Aurora Postgres database that contains the latest known and reliable state of each asset. On top of this, PostNL implemented a relatively simple backend, exposing an API internally to other PostNL business unit that reads and query Postgres and expose the state of the asset to any other business unit that need this information. So we haven't talked so far too much about Amazon Managed Service for Apache Flink. So this is the core, is the stream processor, is the engine doing the work. But before going that, we need to understand why PostNL needed a stateful stream processor for doing this job, such as Apache Flink. Well, first of all, the insights that are needed must be based on the event time. And this is a very important aspect to understand. Event time is just the time when the event was generated by the device and was emitted. It's a timestamp. It's a timestamp usually written in the event itself. And this can be completely different from the time when you receive the record. This can be much earlier, minutes earlier in the case of IoT devices. And also, for this reason, because IoT devices can be disconnected and get reconnected and then burst all the events that were buffered, the events can be delayed So again, event time can be very different from the time you're actually doing the calculation. And events from different devices can very easily be out of order because, I don't know, one device is connected and is sending data in real time while the other one is disconnected and is buffering, and then is sending the data later. And PostNL is actually keeping the events up to half an hour late because they may be relevant. They decided to cut off at half an hour. This is arbitrary, but retaining event to half an hour late. And implementing event time logic or event time semantics, as I should properly say, when events can be delayed in most of the real use cases and can be out of order is not trivial. But luckily, Flink provides primitives to do this out of the box. Also, to get actionable events out of the raw events that are coming from the devices, PostNL is not processing one event at a time. It's not one event in, one raw event in, generating one actionable event. They're actually looking at the history. They're keeping a history of events and emitting actionable event when relevant. And this type of processing is called a stateful aggregation. It means that the application needs to remember the history. It needs to remember what happened in the past for a given duration of time. And, well, this is not too complicated. You can think, well, I can keep it in memory. It's not too complicated to implement, unless you want to provide proper consistency guarantees. And what does it mean? I mean, it's very easy. What happens if the application crashes and you have to restart? If you're just keeping in memory, everything is lost. So, doing stateful processing, stateful aggregation, providing proper consistency guarantees is not trivial. Luckily, Flink provides, again, mechanisms to support this kind of guarantees over stateful aggregation and stateful processing out of the box. This is actually the core feature of Flink. And lastly, but definitely not least, Flink can integrate with multiple systems. We have seen it can consume and produce to Kinesis data streams, but also can read and write to database, to data lake, and many, many other systems. And we have learned how, we have seen how PostNL is already using this and is going to use even more in the future. And PostNL decided to use Amazon Managed Service for Apache Flink as a fully managed offering, a fully managed way of running a Flink job. So Managed Flink offer a serverless experience to the user, so the team can just focus on building, implementing the business logic. They don't have to worry about setting up, deploying, and maintaining and operating Flink clusters. It's also highly available by default. For example, it has availability zone failover in case something happens in one availability zone. You can control the application lifecycle with a single API. So a single API can be used to stop-start application, to update the application configuration, to deploy a configuration change, and to scale the application. The application state, we have learned, is so important because the operations are stateful, is completely managed, and also scaling is completely managed. There is an out-of-the-box auto-scaling you can just enable based on CPU utilization. If it's good for you, you just enable it. Otherwise, because scaling is controlled by a single API, you can very easily implement your own custom auto-scaling based on any metrics you want, or any consideration, even time, and control the scaling of your application. So with Flink, you actually program, you create your business logic, you implement your business logic. How do you do that? How do you program Flink? Well, Flink has a number of programming API. And they differ in terms of level of abstraction and complexity and flexibility. As usual, complexity and flexibility always go together. And you can also program Flink in different languages. Java mainly, but it's actually any JVM language. Customers are using Kotlin, for example, or Python. So starting from the top, the highest level of abstraction is SQL. It's the easiest to learn. Is SQL, very common abstraction, you know, table, joins, very easy to start with. Is also the first one falling short when the use case is not too simple. Actually, the PostNL team started with SQL because the use case looked being simple, but they quickly realized they needed more flexibility. So below, in terms of abstraction, in terms of level of abstraction, SQL, there is table API. Abstraction level is kind of similar in this case. You're still dealing with tables, joins, group by, so same mental model, but in this case is a programmatic API. You program it using either Java or Python. Below that, there is the native API, native programming API of Flink, data stream API. In this case, the abstraction completely changes. You're dealing with streams, you're dealing with windows, you're dealing with keyby to partition the data. This is actually very close to how Flink actually runs the application internally. And the PostNL team quickly realized this was actually the level of abstraction they should start working on. Actually, below that, there is another lower level of abstraction that is just a way of extending data stream API, implementing your own custom operator, that is called process function. It allows you to have the top level of control on everything, effectively. You can control the handling of each single event. You can control what you're putting in the application state, and you can leverage directly watermarks and timer to implement some custom time-based logic, as PostNL did. And actually, PostNL positioned themselves at this level. So they use Java. They had .NET experience before. It was relatively easy for them moving to Java. And they use process function to implement their custom logic. However, as we know, with great power comes great responsibility. So process function gave to the PostNL team the flexibility they needed, but also they were taking on themselves the responsibility that normally, if you're using higher level of abstractions, are taken by Flink. So they have to be sure, they have to test the application thoroughly to be sure no bug was left behind. What we are talking about here is nothing special. What we are talking about here is just applying the common software engineering best practices. So what it is was using CI/CD automation, automated testing at all levels. So from the unit test, integration test, end-to-end test, also soak tests, keeping the application running in the long term to see it was behaving as expected. So, and last point, as we learned, one of the design challenges for the PostNL team was actually to implement a multi-asset support platform, maximizing the reusability of the components and retaining the flexibility they need because of the very diverse asset types they have. So, first of all, they have to generalize the data model. So, for example, the identifier of the data point, of the raw data point, have to contain the information of asset type, the asset ID, but also the sensor ID to support assets that have multiple sensors. Also, because the volume of data from different asset type is very different. Has been mentioned, there are hundreds of thousands of raw cages, while at the moment there are 100, it will be 1,000 of electric vehicles. But the volume of data coming from these different asset types will always be different. Okay? So what they decided was to use a separate Kinesis data stream, one per asset type. This allowed them to scale the Kinesis data stream differently, depending on the volume of data. But because a Flink application can very easily consume from multiple data streams, very easily, they have the ability of having a single Flink application, generalized, consuming and processing multiple asset types, or if an asset types require a particular flexibility that cannot be generalized, have to be custom, they can have a separate Flink application consuming only that data stream and processing whatever is special for that asset type. And finally, we have seen that different asset types have different ingestions, and this has to happen in any complex IoT platform. But what has been done is, after the ingestion, everything was actually going into the same stream storage, into Kinesis data stream as JSON, trying to generalize this and to standardize this as much as possible. And now I will hand over to my colleague Amit to wrap up.
Thank you, Lorenzo. Okay, so let's recap the PostNL's IoT journey we discussed during this session. So PostNL started their IoT journey with a focused solution known as roller cages solution or roller cages tracking. After the successful implementation of roller cages tracking solution, they started adding more and more assets to the IoT platform like tippers or the electric vehicles. Now, with the addition of more and more asset means now they need to ensure the solution which they are using can scale to support multiple asset types and can also handle billions of raw IoT events. So what they did is they migrated the legacy solution to Amazon Managed Services for Apache Flink. The growing number of assets also means that now they need to take care of the maintenance of those hardwares to ensure the solution is reliable, the assets are reliable. Now, talking about the future. So PostNL is now planning to add more and more IoT assets to the IoT platform. For example, handheld devices and many other IoT devices. And not just that, PostNL is also planning to create a digital dashboard to monitor these assets, as in how those assets are performing, if any maintenance is required, whether those assets are working properly or not. And at the same time, they're also planning to use advanced analytics and AI/ML to use the data effectively. Okay, now let's talk about learning and key takeaways from this session. The first, real-time processing is critical for modern logistics. So if you are planning to build a solution, or if you're planning to build an IoT platform to track the real-time IoT asset data, plan to implement the stream processing. Next, design for scale and complexity from start. So while you are designing the solution, ensure that your solution can scale to handle multiple asset types and also the billions or millions of events in future. Third, choose the right architecture components. So it's very important to understand what technology, what programming language, what services you are choosing to build this solution. Next is focus on practical implementation requirements. So you need to ensure the engineering team who is going to work on this solution has the right programming skill and they know the software development lifecycle process. And finally, balance business value with technical complexity. So when you will start adding more and more assets, you need to think about the total cost of ownership, including the maintenance of those hardware versus the return of investment of the application which you are going to build, because this could be a decision maker. Now, if you want to learn more about how PostNL is processing billions of raw IoT events using Amazon Managed Services for Apache Flink, you can scan the first QR code. If you want to learn the service itself, scan the second QR code. And there is also a workshop available. So in case you want to build a POC demo or you want to try the service, scan the third QR code. With this session has come to an end. Thank you, everyone, for joining this breakout session. And before you leave, I would request you to scan the QR code and provide your valuable feedback. That would be helpful. And if you have more questions on PostNL's IoT platform, or if you want to learn more about Amazon Managed Services for Apache Flink, you can reach out to us after this breakout session. Thank you. Thanks, everyone.